All right. So, potential energy, right? If you have an electron that's going around a circle, orbiting a proton has potential energy. It does. So the potential energy of the electron, anybody remember how we it's not kinetic. Yeah.
Don't we use?
We have that chart. That chart like forever ago. Or we can do forces, force times distance. The force? Yeah, thank you. K Q1 Q2 over R squared, yes? That makes sense? And how many objects? Two, right? And work, which is the change in energy, is equal to the force times the distance away, right? So we can always get this stuff as long as we know where one of them came from. Is that okay? That's right. It's all there. It's not stuff. Rachel, too. I don't want cartilage, sir. I want my own shirt. All right. So the potential energy relative to one over R. Yeah. Okay. Now the charges are not just any random charge. We know that the electrons don't have the same charge. Yes. Okay. So let's go with that, and let's say so. I'm gonna say negative E squared over R. Is that okay with everybody? So E is the fundamental charge of an electron or proton. The fundamental charge in quotation marks. Okay. If we assume that we're living at a reference frame where the nucleus is at rest, because it makes our life better, then we can say that the total energy of the system of this electron and the proton, okay, are the potential energy of the electron as it's orbiting and the kinetic energy of the electron. Because the proton isn't going anywhere. So it's got no. Is that okay? Yes? No? Talk to me? Yeah? Yeah? So you got kinetic energy plus potential energy. All of that is of the electron. Just trying to keep track of that. So we know that kinetic energy is described by what formula? 1/2 m. And which m are we talking about? Mass of the electron times the velocity of the electron going around squared. Is that okay? And then we're going to add that negative k e squared over r. And then I'm going to switch gears for just a minute. We're going to come back to that equation in a minute, okay? We're going to go to Newton's second law because I know you've been missing it. Haven't you? It's true, right? What was Newton's second law? What'd you say? Yeah. And this is a centripetal force, right? Is equal to the mass of what kind of acceleration? Centripetal acceleration. And the force that's keeping that electron in its orbit is what kind of force? It is a centripetal force, but what kind of force? Where does it come from? Yeah, that electric attraction, right? The Coulomb force between them. So that's going to be K. I'm going to write it squared. Is that okay? K squared. I'm not going to worry about the negative because if we're just talking about the direction is always inward. Does that make sense? So it's going to be K squared over R squared. K over R squared for the force. Is that okay? Yeah, okay, so don't want to do look at me funny. And centripetal acceleration, what is the, oh, hi, I don't want that. What is centripetal acceleration? What did you say? Yeah. So you got the mass of the electron times v squared over r. Let me pause for just a moment. Is that okay with everybody? What just happened there? No? Okay. Now, straight. Now, because I can, and oh, sounds good. Why wouldn't you want to multiply by 1/2 r? Well, let's do it. Multiply 1/2 r this side 2r is equal to 1/2, oh, that's nice, MEV squared. Ready for the party? Come on in. We're just getting started. Pull up a chair and pull up a piece of paper. Woohoo! All right. Are we okay here? Andrew, why are you like, wow, that's cool? Beyond that, there's another. What's it?
Well, because can't you actually now find the, yeah.
So now instead of plug that. More colors equals one. What? So here we go. We're going to say that the total energy is equal to, so that's going to be K E squared over 2R minus K E squared over R. Well, those are like 1/2 minus 1. You have negative 1/2, right? So the total energy is going to be negative K E squared over 2R. Well, that's interesting. I'm going to put a box around that, but we're not done. Here, why don't you use this? Okay. That's good. But wait, there's more. How many assumptions were there? 4 assumptions, right? So we need to use more of them. I want to use. Yeah, the quantization momentum, right? So MEVR, that's the angular momentum, is equal to this NHR thing. Okay. Well, that's cool. I'm also going to use the equation that we had before Lander decided to multiply things by 1/2. I'm just going to effect on there. Nice and interesting. So the other equation I'm going to use is K E squared over R squared is equal to M V squared and E V squared over R. So I've got 2 statements there. Is that okay with everybody? What just happened? Yeah. And using these 2 equations, I'm going to let you do some algebra. I would like for you to come up with an expression for the radius. Okay? So my recommendation for you would be to solve for V and plug it into the other one. That would be my recommendation to you. Oh no, I lied. That both squared. By that, I'm going to get this by V by R over ME times R and square the whole. Solve them both for V squared and then smash them together and see what comes out if you solve for R. Jack, are you giving up? What are you doing? Oh, okay. Okay. I thought maybe you were like, I'm just going to read history. I don't want to do this algebra. So this is 10. Right? That's why it's classy. Right. I want you to solve for R. I want an expression for R. The mass of the electron times the radius. Yep. R. How's it going? Blindly doing algebra because your physics teacher tells you to. We are. What'd you get? What expression did you get? And then an e squared. Yep. Couple of e's in there. Okay. And so you say, wow, that's pretty. Thanks, Miss Carbeling, for letting us write down a bunch of letters. Let's talk about what this means. Okay? Because the meaning behind it is what it actually means. So again, what were we saying? All we were saying was that the angular momentum is quantized. That was one of the assumptions that Bohr made. And we're taking the expression for energy. And basically what we've done now is to get an expression for the radius at which that electron is transported. Okay. And if we look back at our assumptions, the ones that Bohr made a while ago here, he said that only certain orbits are stable. And what we found is an expression for the orbits that are stable. Because here, this you could rewrite this as n squared times this constant, h bar squared over k e squared. What's that? Okay, are you sure? So m is going to be equal to 1 or 2 or 3, da, da, da. But if n isn't an integer, then this is not a stable orbit. Okay? If we make n equal 1, if we set n equal to 1, that is the smallest orbit, right? That makes sense. And that is what we now call the Bohr radius. Okay? Bohr radius is h bar over k me squared. It has a value. I'm not going to make you plug in 0.0529 nanometers. Okay. We've done measurements since, and this is indeed the radius for hydrogen. This is for hydrogen. Just for hydrogen, yes. Okay. Any other orbit can be expressed in terms of the Bohr radius. It's just going to be n squared times the Bohr radius. Okay. But wait, there's more. 8 more minutes, two more big things. I'm going to take this expression for radius, and instead of having that energy statement that I had up here, an R in it, now I know what R is. Right? So now we can talk about this energy equation because Jack's like, I just want to plug more numbers. Right? Is that what you were thinking? That's how I read it from your face. Okay, let's do it. It's going to be a beautiful thing. Here we go. Combining energy and radius equations together, you're going to get E, the energy of any given radius, n, is going to be equal to, because we have that negative k e squared over 2, and then it was over 2r, right? I'm going to multiply that by the reciprocal of the expression we had before. So that's going to be e squared k m over n squared h bar squared. That's pretty. We can make it a little prettier because there are things that it has in common, right? So like we can throw things in there, throw things together. What do you get when you combine things that are like? Yeah. So that k squared e to the fourth times the mass divided by 2n squared h bar squared. You say, oh, okay, that's interesting. If we plug in, well, I guess we can just leave it in terms of numbers here, just I'm not sure how much to give to you. This is negative 13.6 EV over m squared. Have you heard 13.6 before? Does that sound familiar to you?
Isn't it the first optimization?
It is. Yep, yep. This is the ionization energy for hydrogen. What is ionization energy?
The amount of energy needed to create one.
Right. So, so I find that to pull it off. Right. So that's how much energy it has. Now we're gonna do one more thing. Can. Oh yeah. Oh, of course. How far do you want me to go up? There. Okay. Okay. So postulate number 3, I think it was, or assumption number 3, said that there's going to be radiation, right? That radiation is going to be emitted when we jump from one orbital to another. And there was a piece that I did not write down. I just realized that. So later, are you good? Can I move up now? I'm just going to throw this into the list because I forgot to write this down before. And this is not at number 3. Energy final. Energy initial minus energy final. So the energy that's given off when these jumps occur, not only is there radiation given off, but it's a specific amount of energy, and it's an amount of energy that we will learn about later more. But I'm just going to tell you it's H times S. H is Planck's constant. Okay. Frequency of the radiation. Okay. So I'm going to use that statement and this crazy expression for E to get one more thing. Here we go. Last deal. Rachel, oh, the pink is kind of hard to see. I'll get, let's try this. That's fun. All right, here we go. So, EI minus EF, which we are suggesting is equal to H times F. Okay. We could also say that's equal to H over, well, hold on, let me back up for just a second. We know that the speed of light is equal to the frequency times the wavelength. Is that true? So instead of writing F, I'm going to write C over lambda. So HC over lambda. Is that okay? And then I'm going to take one more step and I'm going to say 1 over lambda, not coincidentally, okay, is going to be equal to then, well, that's going to be, what's what? I know, I am too. This is one of my favorite things all the time. H, like that. We okay so far?
Let's go get that other.
Okay, well, hold on. Let's not get there yet. Let's plug stuff in. We got, you like, come on. All right, so EI and EX. What's going to be EI and EX? And is it all of the denominator, or there's one piece that's going to be the N, right? So everything else is going to stay the same. So I'm going to write this down. So I'm going to say 1 over lambda is equal to, so I'm going to take everything else. So the negative k squared, e to the fourth, make sure I don't lose anything here, me over 2h bar, okay, times h times c. Well, there's one that's h and one that's h bar, right? So we can put them together. We have to have a, oh, it is squared. Thank you. Yeah. This is going to be 1 over n initial squared minus 1 over n final squared. Oh, that's where we get some interesting stuff. And Harry's madly plugging numbers. Someone just.
Are you finding the wavelengths? You can,
So if you plug in all of these numbers, I'll tell you number one, because a lot of really kind of gets but I've done it a number of times. And if you do it carefully, what do you think that value comes out to be? You are correct, Harry. Ding, 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 ding. Yes. This number here turns out to be the Rydberg constant. And that is, it is beautiful. I mean, that's pretty awesome. So again, even though Bohr had some weird assumptions, we're like, we don't know why these are true. This is not insignificant, right? We theory. Okay. And so that kind of we get to theoretically, we I, that's as far as I wanted to get today. And look at that, it's time for it to be done.